Welcome back to the library. Or, I should probably say a library. If you're looking around the virtual studio with us today, you'll see the backdrop is a little different.
It's definitely got a different vibe.
It's cozy, all the mahogany, the leather armchairs, that classic smell of old paper that I really wish we could transmit over audio somehow. But have you noticed the books themselves?
They're moving. They're not staying put.
Exactly. They're rearranging themselves on the shelves. It's like completely dynamic. You'll see a book slide out from the top shelf, float down, open itself for a second, then just tuck itself right back in.
It's got a bit of a magical, almost sci-fi feel to it.
It really does. A little Harry Potter, a little bit of something from the future, and honestly, it is the perfect visual metaphor for what we are going to be talking about today.
Absolutely. It sets the stage perfectly.
We are doing a deep dive into a really comprehensive survey. The title is A Survey on Test Time Scaling in Large Language Models.
And it's a fascinating piece of research. It pulls together work from authors at City University of Hong Kong, McGill, a whole host of other top institutions. And, it really addresses the single biggest elephant in the AI room right now.
Which is the status quo problem.
Right. For the last, 5, maybe even 10 years, the answer to pretty much every single question in AI development has been exactly the same. Just make it bigger.
The era of pre-training scaling.
Precisely. If your model isn't smart enough, well, double the parameters. If that doesn't work, double the data you feed it. Build a bigger cluster of GPUs. Burn enough energy to power a medium-sized European country.
It was a very brute force approach.
It was. The guiding philosophy was just so simple. If you read more books, you get smarter. It was basically memorization on a planetary scale. But, and this is the big but, we are hitting a wall.
That curve is definitely flattening out. I mean, we're kind of running out of high-quality human text to feed these things.
We really are. We've scraped the entire internet, Reddit, Wikipedia, the whole digitized library of human history, and we've just fed it all into the machine.
And frankly, just from a purely economic standpoint, my laptop can't run a 100 billion parameter model. I don't think anyone's can, really. The hardware requirements are they're absurd for the average person or researcher.
Absolutely. So the whole industry is pivoting. We're seeing a shift from training a smarter brain to something more subtle, more like giving the brain time to think.
And that is the absolute core of what this paper calls test time scaling, or TTS.
It's the shift from simply memorizing answers during that long, expensive training phase to actually reasoning through them during the inference phase. That's the actual moment you ask it a question.
I want to pause on that distinction because I think it's just so crucial for everything we're about to discuss. The paper uses an analogy that, for me, perfectly frames this entire conversation. It comes from psychology, and if you've ever read Thinking Fast and Slow, you know exactly where this is going.
Daniel Kahneman's System 1 and System 2, a classic.
Right. Let's really unpack this because I think it explains why our current AI can sometimes feel incredibly smart and, at other times, just shockingly stupid.
So System 1 is your fast brain. It's your instinctive brain. It's the autopilot. If I ask you, what is 2 plus 2? You don't really calculate it. You don't perform arithmetic in your head.
No, the answer just appears.
It just appears. It's 4. It's a reflex. You've seen that pattern so many times that the answer is hardwired.
Yeah, there's no sensation of gears turning in my head. Feels totally instant.
Because it is. There isn't any deep thought. It's all pattern matching. And that is what standard large language models, the GPT-3s, the early versions of GPT-4 have been doing all along.
That next token prediction is basically just a high-speed reflex.
It's exactly that. It's looking at a sequence of words like the sky is, and instinctively, reflexively knowing the next word is probably blue. It's not thinking about the atmosphere or the physics of light refraction. It's just completing a pattern it has seen millions of times.
But then there's System 2.
And System 2 is the complete opposite. It's slow, it's deliberate, it's logical. It's what you engage when I ask you to solve a complex riddle or, say, write a Python script to scrape a website with a really weird structure.
Or plan a travel itinerary for 5 people with different allergies, all under a strict budget.
Exactly. System 1 fails immediately on a task like that. If you try to answer instantly, you'll just blurt out nonsense. You have to engage System 2. You have to stop, take a breath, break the problem down into smaller parts, check your work, and then you speak.
And that is the mission for today's deep dive. We're going to unpack how AI researchers are, in a sense, forcing these models to use their System 2. We're going to look at this massive survey that breaks the whole field down into 4 key axes: what to scale, how to scale, where to apply it, and maybe most importantly, how to measure if it's actually working.
And it's not just about waiting longer for an answer. That's a common misconception. It's about structuring that waiting time. It's about building an architecture of thought.
So let's get into the core philosophy first. Why wait to think? Because, in this world of instant gratification, a chatbot that pauses for 10 seconds feels,
Mm.
well, it feels broken, right?
It does.
We're so used to instant answers. When I type into Google or ChatGPT, I want to see that text start streaming back before I've even finished blinking.
It feels broken only if you expect it to be a search engine, a fact retrieval machine. If you expect it to be a reasoner, then the pause is not just acceptable, it's essential.
That's a great point. It's about reframing our expectations.
And the paper highlights these incredible findings from researchers like Brown et al. And Wu et al. That show something that really turned the field on its head. Increasing the amount of compute you use during the answer generation, during inference, it yields performance improvements that are just as consistent and predictable as the old scaling laws we saw with model size.
Okay, that right there is the aha moment for me. We have been so obsessed with building a bigger and bigger brain. We thought the only way to get smarter was to add more neurons, more parameters.
But it turns out that's not the whole story.
It turns out that a medium-sized brain that actually stops and tries hard can outperform a giant genius-level brain that's just blurting out the first thing that comes to its mind.
Precisely. I mean, think about it in human terms. Who would you trust to solve a complex engineering problem? Would it be a certified genius who answers in 1 second without even looking at the data?
No way.
Or would it be a reasonably smart but very careful engineer who spends a week analyzing the schematics, testing out different theories, and meticulously verifying their math every step of the way?
I'm taking the careful engineer every single time.
Yeah,
Not even a question.
of course. And if you look at Figure 1 in the source material, they do this great job of contrasting these two paradigms. The old way, pre-training, scaling, building that giant brain, is just terribly resource inefficient.
And the feedback loop is incredibly slow, painfully slow.
It's glacial. You train a model for 6 months, maybe longer. You spend millions of dollars. You release it. Then you realize it has some subtle bias, or it's actually terrible at math, or it hallucinates legal cases. Well, guess what?
Too bad.
You can't just patch it.
Not easily. You often have to start over from scratch or do another massive, expensive fine-tuning run. And let's be honest, the only participants in that game are the big tech companies with billion-dollar budgets.
Whereas this new paradigm, test time scaling.
It's so much more agile. It's resource efficient. You don't need to retrain the base model at all. You just change how it behaves when it answers a question. And that democratizes the research.
That's huge.
It is. A university lab or a small startup can now tinker with these inference strategies, prompting techniques, search algorithms, without needing their own dedicated power plant and a warehouse full of NVIDIA H100s to train a foundation model from the ground up.
And we are seeing this live in the wild right now. This isn't just some theoretical lab experiment. We have OpenAI's O1 model and, more recently, DeepSeek R1. These models are famous, or maybe infamous, for showing you their thought process.
Exactly. If you've used them, you've seen this in action. They don't just give you the final block of code. They have a little drop-down or a separate window where you can see the model saying things like, wait, let me double-check that. Actually, that library is deprecated. Okay, I should probably try this other approach instead.
It backtracks. It literally argues with itself in real time.
And that is TTS in action. They are reasoning by allocating more tokens, more computation to the thought process before they generate the final output. So the first big question the survey tackles is, what exactly are we scaling here? What is the actual form of this additional computation?
How does this thinking actually take shape?
And the paper breaks this down into 4 main buckets, and I think we should walk through them because they give such a clear picture of how we can start to engineer intelligence. The first one is called parallel scaling.
Or, as I like to call it, the wisdom of the crowd approach.
That's a great way to put it. The idea here is deceptively simple. Instead of asking the model to generate one single answer, you ask it to generate, say, 100 different answers simultaneously.
Now, I can hear a listener asking, why on earth would I want 100 different answers? I mean, if the model is a computer program, shouldn't it give me the same answer every single time? If I type 2 plus 2 into my calculator 100 times, I get 4 every time.
Ah, but that's the key. LLMs are not calculators. They are probabilistic engines. They are built to predict the next word based on likelihood. And there's a setting, a parameter called temperature, that controls randomness. If you turn up the temperature, the model will take slightly different paths through that massive probability space each time it generates.
So for a really complex math problem, If you only generate one answer, it's a pretty chance you'll hit a wrong path somewhere along the way. You slip on a digital banana peel, so to speak.
Exactly. Maybe it misinterprets one word in the question, or it makes a tiny arithmetic error in the very first step.
Hmm.
If you only generate one sample, you're just stuck with that error. Your entire result is wrong.
But if you generate 100 different answers,
Then you increase what the paper calls coverage, and that's the probability that at least one of those 100 answers is correct.
it's kind of like buying lottery tickets. If I buy one ticket, my odds are terrible. But if I buy 1,000 tickets, my odds of holding at least one winning ticket go up drastically.
That's the perfect analogy. But there's a catch, and this is why parallel scaling isn't some magic bullet that solves everything. If I have 1,000 lottery tickets, I still have to find the winning one. I can't just walk up to the cashier with a giant bucket of paper and say, "Here, you check these."
Right. Parallel scaling is useless if you can't efficiently and accurately identify the winner from the crowd. You need some kind of aggregation mechanism.
And the most common method for that is something called majority voting, or self-consistency.
It's like democracy for algorithms.
Basically, yeah. If 80 out of your 100 generated answers say the final result is 42 and the other 20 are just a random mess of numbers like 7, 155, or even the word banana, you can be pretty confident that the answer is 42.
That makes perfect sense for things with a single verifiable answer. Math problems, multiple choice questions, things like that. It's been shown to be remarkably effective.
It has. But what about more open-ended tasks? What about writing a novel? Or writing a complex piece of code? Or summarizing a dense legal document?
Yeah, majority voting just completely falls apart there. You can't just average out 100 different essays and hope for the best.
You can't. If half the essays are tragedies and the other half are comedies, merging them doesn't give you a masterpiece. It gives you an incoherent mess. And that brings us to the second bucket from the survey, sequential scaling.
The refining process.
And this is so much closer to how humans actually work on complex, creative, or logical tasks. We don't write 100 drafts of an email simultaneously. We write one draft, we read it over, we critique it, and then we rewrite it.
The paper calls this System 2 emulation. It's iterative. Your state at time n+1 depends directly on your state at time n. You are consciously building on top of your previous thoughts.
Exactly. You are explicitly directing the computation. And there are techniques like self-refine that are huge here. You ask the model to generate an answer. Then, and this is the crucial step, you feed that answer back into the model with a new prompt, something like, critique this answer you just gave me for logical fallacies and factual errors.
It's such a weird concept when you really think about it. You're asking the model to be its own harshest critic, to find flaws in its own work.
And it works surprisingly well. The model is often better at checking work than it is at doing the work from scratch, just like a lot of humans. So you get this critique, and then you feed that back in and say, okay, great, now rewrite your original answer, but fix all those errors you just pointed out.
It's like the difference between me trying to write this whole script in one go versus me writing a rough first draft and then spending a few hours editing it. The parallel method would be like me typing on 100 different laptops at once and just hoping one of the scripts turns out good.
Which is madness.
Total madness. The sequential method is me taking one script and carefully refining it until it's great.
And the research shows that this sequential scaling is particularly good for tasks that require maintaining a long, fragile chain of logic. Think about a multi-step math proof or a complex coding function. If you make just one mistake in step 2, the whole thing completely collapses.
That's what they call error propagation.
Exactly. In parallel scaling, if step 2 is wrong in one of your samples, that entire sample is just trash. It's a lost cause. In sequential scaling, you have the chance to catch the mistake in step 2, fix it, and save the entire output.
But wait a second, why does it have to be one or the other? Can't we have the best of both worlds here? Can't we generate multiple options and refine them iteratively?
Now you're thinking like an AI researcher. And that is exactly what the third bucket is, hybrid scaling.
The search party approach.
This combines the divergent exploratory thinking of parallel scaling with the convergent refining and critical thinking of sequential scaling. And the most famous example here, the one everyone's talking about, is the tree of thoughts, or TOT.
I love tree of thoughts. It's such an intuitive way to visualize the process. It frames thinking as a branching path, like exploring a maze or a decision tree.
Let's walk through an example. Imagine you're playing a game of chess. Or, to make it simpler, imagine you're planning a dinner menu for a big party with picky eaters. You start by considering 3 possible main courses. That's your parallel scaling. You diverge.
Okay, let's say roast chicken, a taco bar, or pasta.
Perfect. Then for each of those main branches, you start to look one step ahead. That's the sequential part. You think, okay, if I commit to the taco bar, I'm going to need fresh cilantro. Do I have any cilantro? No. Is the grocery store still open? No.
So I stopped thinking about the tacos. That branch is a dead end. I prune that branch from my thought tree.
You prune it, exactly. You cut off the dead ends and you allocate your precious mental compute power to exploring the more promising branches deeper. Maybe the pasta path looks good, so you start thinking about possible sauces, marinara or pesto. Then you realize you don't have any tomatoes for the marinara, so you prune that sub-branch and focus all your attention on the pesto.
And this uses classic computer science algorithms, right? Things like breadth-first search or depth-first search.
Or even more advanced ones like Monte Carlo tree search, MCTS, which is the algorithm that AlphaGo used to beat the world's best human Go players.
So we're literally applying game-playing algorithms to the process of thought itself. We're treating tasks like write a good summary or solve a math proof as a game where we are searching for the winning state.
We are, and it's incredibly powerful, but
Yeah.
it's also very heavy. It implies that there's an external controller, a Python script, or some other program that is guiding the model, telling it when to branch, when to stop, when to evaluate, when to prune.
It's not native to the model's own thinking process.
Exactly. It's like a micromanager standing over the employee's shoulder saying, okay, now try this, no, stop that, now go over here. It's not autonomous.
Which brings us to the final and maybe the most exciting and futuristic bucket, internal scaling.
The implicit thinker.
This is the domain where models like DeepSeek R1 and OpenAI's O1 really live.
Yeah.
They aren't being guided by some external Python script that's running a tree of search algorithm. They're doing it all autonomously.
This is the holy grail of this research area. Internal scaling means the model has learned, within its own neural network parameters, how to allocate its own thinking time. It generates what are often called thought tokens.
Let's clarify what thought tokens are. These are the strings of text we sometimes see hidden behind a thinking or show work drop-down in the user interface, right?
That's right. To the model itself, they are just tokens in a sequence, no different from the final answer. But functionally, they serve as an internal scratch pad. The model might produce thousands of these thought tokens, its own internal monologue, before it produces a single word of the final answer.
It's literally having a conversation with itself, debating its own points, checking its own work, backtracking all within a single generation process.
And the reason the survey says this is the future is because it allows for dynamic allocation of compute.
That's the key.
It's everything. If I ask a model with true internal scaling a simple question like, what is the capital of France? It shouldn't waste time and money thinking about it. It should just instantly say Paris.
It stays in system one.
Right. But if I ask it to solve the Raman hypothesis or debug a complex kernel panic log from a server, it should settle in, get comfortable, and generate 10 million thought tokens if it needs to. It doesn't need a human to tell it, please think step by step. It knows, based on the query, how hard the problem is.
It's automating that switch between system one and system two. It knows when to concentrate and when it can just chill out.
And that leads us to the next big question the survey tackles. How do we actually make them do this? Because a standard off-the-shelf model doesn't just wake up one day wanting to think deeply. They're designed to be lazy. They want to predict the next token as fast as possible and take the path of least computational resistance.
This is section 3 of the survey, the toolkit, how to scale. And they divide this into two main approaches, inference-based, which means no extra training is required, and tuning-based, which means we're actually changing the model itself.
Let's start with inference-based, because that's what most users and most developers can start doing right now without spending millions of dollars on GPUs. The simplest method is what the paper calls stimulation.
Which sounds very fancy, but often just boils down to clever prompting.
It can be. The classic chain of thought prompting, just adding the phrase, let's think step by step to your prompt, is a form of stimulation. You are stimulating the model to output its intermediate reasoning steps. But there are more aggressive and frankly weirder forms.
Like the decode strategy. The source mentions injecting filler tokens. This one really blew my mind a little bit.
It's a fascinating hack. The idea is that sometimes a model knows the answer, or it can find the answer, but it needs more computation time to properly organize the output. But the architecture of a transformer model forces it to output a new token immediately on every forward pass.
It's like being a guest on a live TV news show. You can't just sit there in dead silence for 10 seconds while you think. You have to say something.
Exactly. So what do humans do on live TV when they need a second to gather their thoughts? They say, or, well, that's a very interesting question, or, Let me see.
They filibuster to buy time.
They filibuster their own brain. And we can force models to do the exact same thing by instructing the model to output a sequence of meaningless tokens, like a series of dots or some filler phrase. You are physically buying the GPU more time.
You're forcing it to run more processing cycles.
Yes. For every filler token it generates, the model is processing the entire context, running all its layers, and updating its internal hidden states. It pushes the meaningful final answer tokens further down the sequence, which allows more layers of computation to run on the context before the final decision about the next real word is made.
So it's literally the digital equivalent of saying, to buy yourself enough time to sound smart.
That's a great way of thinking about it. The survey also mentions a latent strategy, where the model does all this thinking in the hidden vector space, the raw mathematical representation of language, without ever outputting any text. But that's much harder for us to interpret and debug.
Okay, so we can stimulate the model to think, but thinking is pretty useless if you're just thinking the wrong thoughts over and over. You need some kind of guardrail. You need verification.
Verification is the critical guardrail. The simplest form is outcome verification, just checking the final answer. In the world of coding, this is easy. You just run the code. Does it compile? Does it pass the unit tests? If it crashes, you know it's wrong, and you can tell the model to try again.
But for a reasoning task, it's much harder. You can't just run an essay or a philosophical argument to see if it's correct.
Which is precisely why process verification is such a hot topic in research right now. This is often done with something called a PRM, a process reward model. Imagine a math teacher who doesn't just grade the final number at the bottom of the page, but who checks every single line of your equation.
So if you make a simple addition mistake on line 3, the PRM flags it immediately.
Right. And then the model doesn't waste time in compute, continuing a long calculation that's already doomed to fail. It can stop, backtrack to the point of the error, and try a different path. It makes the whole search through the tree of thoughts much, much more efficient because you aren't wasting time exploring rotten branches.
And then you have search and aggregation, which we touched on before with tree of thoughts, majority voting. These are the core mechanics of how you navigate that vast thought space and combine the results.
But the survey makes it very clear that the real heavy hitters, the O1s and the R1s of the world, aren't just using these clever inference tricks. They are using tuning-based approaches. They are fundamentally modifying the model itself.
This is where things get really technical, but also really interesting. We're talking about SFT-supervised fine-tuning and RL reinforcement learning. Let's unpack SFT first. Specifically, this idea of distillation.
Distillation is a massive trend right now. The process is this. You take a huge, powerful, smart model, like a GPT-4 or a Claude 3.5 Sonnet, and you force it to think through very hard problems using all those inference tricks we just discussed. You make it use a tree of thoughts, you make it verify its own steps.
So you're basically capturing its internal monologue as it solves a problem.
You're capturing its thought traces, the entire step-by-step reasoning process. Then you take a much smaller, cheaper, more efficient model, something you could potentially run on a specialized chip or even a high-end laptop, and you train it on those traces.
It's like you're showing the student the professor's detailed lecture notes.
It's even better than that. You aren't just showing the student the final answer key. You are showing them exactly how the professor arrived at each answer. And what's remarkable is that these small models can learn to mimic those reasoning patterns.
They learn the process, not just the fact.
Exactly. And this is how we get these incredibly powerful yet efficient small models. It's not that the small model is some kind of innate genius. It's that it has perfectly memorized the reasoning patterns of a genius.
But eventually you run out of professor notes, or you hit a problem that even the professor can't solve. Distillation has a ceiling, right? The student can never really surpass the teacher.
That's its fundamental limitation. And that's where reinforcement learning comes in. The survey calls it the engine of internal scaling.
This is the real frontier.
It is. RL allows the model to discover novel reasoning strategies that humans, or even the powerful teacher models, might not have ever used or thought of. And the survey highlights DeepSeek R1 as a prime case study here.
They use something called reward model-free RL for some parts of their training, right? Why is that so significant?
Well, the traditional way to do RL for language models is with the judge model, which is usually called a reward model. Its only job is to look at the AI's output and say, good dog or bad dog, by giving it a score. but training that judge is really, really hard.
How do you teach a model what good reasoning even looks like if the problem is at the edge of human knowledge?
That's the problem. If the AI you're training is smarter than the judge model that's grading it, the judge actually holds it back. It can't appreciate novel or more complex solutions.
So DeepSeek R1 just got rid of the judge.
For certain domains where it's possible, yes. They utilized verifiable ground truths instead.
Domains like math and code.
Exactly. In mathematics, the final answer is either right or wrong. There's no ambiguity. You don't need a complex AI judge to tell you that. You can write a simple, rule-based script. If the model's final answer matches the correct answer, it gets a big reward. If it gets it wrong, it gets no reward. Simple as that.
And here's the magic part the source mentions. DeepSeek found that if you just reward the correct final outcome, the model automatically learns to think longer and produce more reasoning steps for harder problems.
It's an emergent behavior. This is the part of the paper that gives me goosebumps every time I read it. They did not explicitly program the model with a rule that said, think for 500 tokens on this type of problem. They just said, get this hard math problem right.
And the model figured out the strategy for itself.
Through thousands and thousands of trial and error attempts, the model realized on its own that if it generated a long chain of reasoning, if it broke the problem down, checked its signs, reread the question carefully, it got the reward more often.
But it literally learned to think.
It learned that contemplation is a successful survival strategy within that training environment. It learned that engaging System 2 is better than relying on System 1 for survival.
That is just wild. It evolved the behavior of contemplation because that was the most efficient evolutionary path to maximizing its reward.
It's the evolution of instinct simulated in silicon. And to make this process computationally feasible, they used advanced techniques like GRPO group relative policy optimization.
Can you just briefly, for our more tech-savvy listeners, explain what problem GRPO solves?
Sure, standard RL methods like PPO, which is very popular, need to keep a copy of the model to act as a critic or a value model that effectively doubles your memory requirements. So if you have a 70 billion parameter model, you need another 70 billion parameters just for the critic. That's incredibly expensive.
And GRPO gets around that.
It does. It gets rid of that separate critic model. Instead, it generates a group of outputs from the main model, scores them all relative to each other, and then updates the model's policy based on the group's average performance. It's much, much lighter on memory, which allows you to scale this kind of training up to massive models.
So it's efficient, it's emergent, and it's clearly working. But where does this actually matter in the real world? This brings us to section 4 of the paper, the battlegrounds. Where are we actually seeing this applied?
Well, the primary battleground is the obvious one, reasoning-intensive tasks.
A logic zone.
Math, code, and hard science. The survey calls mathematics the fruit fly of AI research.
What does that mean? It's the lab rat we test everything on first.
Precisely. It's the perfect testbed because it's so precise. Unlike writing a poem where good is subjective, a mathematical proof is objectively either right or wrong. Benchmarks like AIM, the American Invitational Mathematics Examination, or the Math 500 dataset are the standard tests here.
And in those problems, one tiny slip-up in logic just ruins the entire chain.
It does. Standard models that rely on System 1 fail here constantly. TTS is absolutely essential because you have to be able to check your own work.
And code is a similar story.
A very similar dynamic. One syntax error, one misplaced semicolon, and the whole program breaks. TTS allows the model to essentially compile the code in its head or run a mental linter, catch an error, and fix it before it ever outputs the final text. We see this being tested in benchmarks like SWE Bench, which tests real-world software engineering capabilities.
But the survey also mentions agentic tasks. This feels like the next big frontier. This moves beyond just answering questions to actually doing things in the world.
This is where it gets really real. An AI agent isn't just answering a question, it's actively interacting with a digital or even a physical environment. You can look at benchmarks like WebShop or WebVoyager. In these tasks, the AI has to browse a simulated e-commerce website, find a product with a specific set of attributes, add it to the cart, and check out.
It requires planning, a whole sequence of actions. First, I'll search for shoes, then I'll filter by size 10, then I'll check the shopping cart.
And it requires dealing with complex feedback loops. Real-world scaling is much harder here because getting feedback takes time and exploration. In a math problem, I know instantly if my step was right or wrong. In a web browsing task, I might have to click on 10 different links before I even realize I'm on the wrong website entirely.
So TTS for agents involves simulating that environment.
It involves planning ahead. It's like running a simulation of the world in its head before it clicks the mouse. If I click this button, what will likely happen? Is that outcome what I want? It's a constant look-ahead process.
There's one more application area they mentioned that I found really fascinating. Evaluation tasks. Using AI as a judge.
This is a bit meta, but it's absolutely crucial. As these models get smarter and smarter, we humans are having a harder and harder time grading them. If an AI writes a complex proof in quantum physics, I certainly can't grade it. I have no idea if it's correct. So who grades the superintelligence?
Another even smarter superintelligence.
Or the same model just taking its time. If you apply test time scaling to make a model a better grader, you can improve the entire AI development ecosystem. The survey points out that if a judge model thinks for longer before it assigns a score to another AI's output, that grading becomes fairer, more nuanced, and more accurate.
It's like the difference between a teacher taking the whole weekend to thoughtfully grade an essay versus speed grading it on the bus ride home. The thoughtful grade is always going to be better.
Exactly. And better grading means better training data for the next generation of models. It creates a positive feedback loop for the entire field.
So we're applying this powerful technique everywhere. But how do we actually know if it's working? This is Section 5, measuring success. And it's not just about raw accuracy anymore, is it?
No, not at all. The metrics have had to evolve along with the techniques. We obviously still have pass at 1. Did the model get it right on the very first try? That's the standard classic test. But for parallel scaling, we have to use pass at k.
Right, that's the potential metric.
It measures the upper bound of the model's capability. Did any of your, say, 100 different answers hit the mark? It tells us if the correct answer is even accessible to the model. If the answer is in there somewhere, we know the model can solve it. The challenge then just becomes finding the right path.
But my favorite new metric from the survey is cons at k, the consensus score.
The majority vote? Yes. This is a measure of reliability. If 90% of your generated thought paths all lead to the exact same final answer, that implies the model is very confident. But if your thought paths are all over the place, if one leads to the answer flabby 2, another to 7, and a third to blue, then you know the model is confused and not very reliable on this problem.
But there's always a cost. We can't just ignore the efficiency metrics.
This is the flip side of the coin, the token cost. All this verbose reasoning is expensive. Every single token, whether it's part of the final answer or just an internal thought, costs compute, time, and money. If a model writes a 10-page novella of thoughts just to tell you that 2 + 2 = 4, that's just a colossal waste. It's bad engineering.
The survey has a specific, very human term for that, overthinking.
And it has one for the opposite problem, underthinking.
I think I can relate to both of these very heavily.
Fox, don't we all? The underthinking score is a fascinating metric they've developed. It measures how often a model actually had a correct intermediate thought. It was on the right track, but then it abandoned that correct thought and ended up giving a wrong final answer.
Oh, that's a tragedy of reasoning. It's like when you have the right answer on a multiple choice test, but you second-guess yourself, erase it, and write down the wrong one.
It's the exact same phenomenon, and overthinking.
That's when the model just keeps verifying a simple problem excessively.
Yeah, like checking 2 + 2 5 different times using 5 different methods. The goal of TTS isn't just more thinking, it's optimal thinking. And this leads to research into controllability metrics. Can we force the model to think for exactly 10 seconds or for exactly 500 tokens and no more?
And right now, that's still pretty hard to do. It's a bit of a black box.
Which leads us nicely into the final big section of the survey, challenges and practical guidelines. So if you're a listener right now wanting to actually implement this, maybe you're a developer or a researcher, the survey offers some really solid hands-on advice.
A how-to guide for making your AI think harder.
And rule number 1 is start small. Do not jump straight to trying to train your own reinforcement learning cluster from scratch. That is just a recipe for burning money.
Use prompting first, the stimulation technique.
Exactly. Just tell the model to think step by step. See what happens. If that fails, then try parallel scaling. Generate 10 different answers and take a majority vote. That simple technique is often enough to boost performance by 10 or 20% on really hard tasks.
And if you have the resources and the need for more power,
then you can move up the ladder to internal scaling. You can try fine-tuning on reasoning traces. But the survey gives a very important warning here. There is no free lunch.
I love that phrase. It's the economist in me.
It means that the best method always depends on the hardness of the question. For simple queries, all of this TTS machinery is a complete waste of time and money. If you use a deep reasoning tree to answer, "What time is it?" you're just needlessly warming the planet.
But for the hardest questions, simple prompting won't be enough.
It won't even scratch the surface. You'll need the heavy machinery of Monte Carlo tree search or reinforcement learning. And even then, there are open challenges. The survey mentions coverage saturation.
Right. In parallel scaling, generating 1,000 samples might not actually be any better than generating 100.
You hit a point of diminishing returns, you're just generating the same few wrong answers over and over again from slightly different angles.
And then there's error propagation in sequential scaling.
The fragile chain of logic. If step 1 is wrong, then step 10 is almost definitely going to be wrong. The whole chain is poisoned from the start. We need better ways for models to recover from errors mid-thought.
And the really big one, the one that keeps people up at night, the black box of internal scaling.
This is the big philosophical and practical challenge. If the model is doing all its thinking in hidden states or in a massive, unreadable block of thought tokens, how do we debug it? How do we really know it's not hallucinating its logic? If the final answer it gives is correct, but the reasoning it used was because the aliens told me so, do we trust that model?
That is a genuinely terrifying thought, getting the right answer for completely the wrong reason.
It happens, and as we scale these models up and they tackle more complex problems, catching those kinds of logic hallucinations becomes harder and harder because the logic itself becomes more complex than we humans can easily follow or verify.
So to bring this all together as we wrap up, we are witnessing a fundamental shift. The survey calls it a move from memory to reasoning.
I think that sums it up perfectly. The pre-training era was all about memory. It was about reading the entire internet and remembering as many facts as possible. Test time scaling is about reasoning. It's about taking that stored information and actually using it to solve novel problems.
It feels like the model is finally growing up. It's finished its schooling, which was the pre-training phase, and now it's out in the workforce, which is the inference phase, having to actually figure things out on its own.
That's a great way to put it. And the implications of this shift are massive. It suggests that we might not actually need exponentially bigger models to get to AGI or artificial general intelligence. We might just need models that know how to use the intelligence they already have more effectively.
The source material ends with a really provocative thought. It talks about DeepSeek R1 tautology and suggests we should start treating a fine-tuned reasoning model almost like an independent agent.
Yes. And here's the thought I really want to leave everyone with today. We've talked a lot about System 1, which is instinct, and System 2, which is reasoning. In humans, when you learn a complex new skill like learning to drive a car, it starts out as a purely System 2 task.
Right. You are hyper-aware of everything. Your hands are gripping the wheel at 10 and 2. You're constantly checking your mirrors. You're consciously thinking, okay, I need to put my turn signal on now. It's slow, it's deliberate, and it's mentally exhausting.
But then, eventually, after months or years of practice...
Eventually, it becomes System 1. You can drive home from work and not even remember the trip. You don't reason through it anymore. You just do it. It's automatic.
Exactly. The slow, deliberate System 2 process gets distilled down into fast, efficient System 1 intuition. So the final provocative question the paper leaves us with is this. If test time scaling allows our models to simulate and practice System 2 thinking, will this eventually be distilled back down into System 1 for them as well?
Whoa. So will the complex multi-step logic chains of today become the instant, intuitive, reflexive answers of the AI of tomorrow?
Are we essentially automating the very evolution of instinct? Are we building a machine that, through practice, learns to execute incredibly complex logic as a pure reflex?
That is a mind-bending concept. The idea that something like calculus or debugging complex code could one day just become an instinct for a machine, requiring no conscious thought at all.
I think we might be. And if and when that happens, the very distinction between thinking and knowing might completely disappear for these models.
Wow. Okay, on that note, I think I need to let my own System 2 cool down for a bit. My brain is definitely overheating after that.
Chuckles. Take a break. Best not to overthink it.
To all our listeners, thank you for joining us in the library today. If you enjoyed this deep dive into test time scaling, maybe take a moment to pause, reflect, and perhaps even verify your own subscription settings.
We'll see you next time.
Bye, everyone.